Okay, let's be honest for a second about the state of, modern manufacturing.
Right.
If you are still picturing that old Dickensian factory floor steam, sparks, people just mindlessly pulling levers, you are living in a different century.
Completely. I mean, that image is just ancient history.
It is. But even if you update that mental image to, say, robots and assembly lines, you're still kind of missing the point. We aren't just talking about production anymore.
No, not at all.
We are talking about a high-stakes strategy game. It's no longer just, can we build this? It's, how do we engineer this to be virtually indestructible, hyper-efficient, and essentially self-aware?
Exactly. It's that shift from pure volume to value. It's about dominance through detail.
So today we're doing a deep dive into strategic manufacturing product enhancement methods. We're pulling from a really comprehensive set of insights from First Mold, and they're heavy hitters in injection molding and CNC machining.
They really are.
But here is the mission for this deep dive. We aren't just going to give you a glossary of terms. You know what a factory is.
Right. We're assuming, the basics.
We want to look at the 5 strategic levers that actually move the needle on quality and brand presence. We're talking about the intersection of, well, philosophy, digital infrastructure, and advanced material science.
It is a fascinating cross-section because when you look at a truly premium product, a medical device or a high-end car part, you aren't just seeing the object. You're seeing thousands of micro-decisions.
A philosophy of perfection.
That's it. You're seeing a philosophy.
So let's unpack that philosophy first. The source material leads pretty heavily with lean manufacturing. Now, everyone listening has probably heard of lean. It's been a buzzword for decades.
Well, yeah.
But reading through this, First Mold isn't talking about it as just cleaning up.
No, and that's where a lot of people get it wrong. They think lean is just about, tidying up the shop floor.
Right.
Lean is essentially a relentless war on waste. But the real nuance is in how you define waste.
The source lists the 8 types of waste. And sure, you have the obvious ones like defects and excess inventory. But the one that really stood out to me, especially for something like injection molding, is waiting time.
Waiting time is insidious. It sounds so passive, like someone's just standing around. But in a high-speed manufacturing environment, waiting is incredibly expensive.
How so?
Well, if a robot arm is out of sync by half a second, or a mold isn't ready when the plastic resin is at the perfect temperature, you aren't just losing time.
You're degrading the material.
You were degrading the materials. Exactly. That resin is sitting there cooking in the barrel.
Which leads to bad parts later?
Inconsistent parts, yeah. So when they talk about eliminating waiting time, they're talking about synchronizing the entire line down to the millisecond. It's more like a ballet than a cue.
Another form of waste the source highlighted, one I think often gets ignored in all the tech talk, is underused talent.
Yes, the human capital waste.
It feels surprisingly soft for a manufacturing strategy, but it makes so much sense. If you have an operator running a CNC machine who knows the tool path is inefficient, but the system doesn't let him speak up,
you are just burning money. You absolutely are. That operator is the one closest to the cut.
right?
If your company culture suppresses their feedback, because, engineering knows best, you're missing out on all these tiny optimizations that compound over thousands of cycles.
So lean is about respect as much as it is about speed.
I think so, yeah.
Now, you can't really talk about lean without talking about its sterner sibling, Six Sigma.
Oh, the other side of the coin.
And we all know the benchmark, 3.4 defects per million opportunities. That's the Six Sigma standard.
Different one.
But let's be real here. Achieving that in a high-mix, low-volume environment like First Mold describes is a totally different beast than, say, on a line making the same bolt for 10 years.
Oh, it's exponentially harder. When you are switching molds every few days, dealing with different shrinkage rates of polymers, different humidity levels in the air, the variables are everywhere. That 3.4 number isn't just a goal. It's a mathematical obsession.
The source breaks down the DMAIC framework. Define, measure, analyze, improve, control. Which sounds like pretty standard project management.
It does, until you apply it to a physical defect.
Okay, so walk me through it.
Let's take a real-world example. Say you have a plastic housing that's warping slightly as it cools. That's the define phase. You've defined the problem.
Okay.
The measure phase isn't just, looking at it. It's deploying sensors to map the thermal gradient of the entire mold.
You're gathering hard data.
Hard data. Then analyze is looking at that data and realizing, oh, look, cooling channel B is partially blocked, or the injection pressure is spiking.
So you aren't guessing. You're not just tweaking a dial and hoping for the best.
Never guess. You improve by fixing that root cause. And then, and this is the most important part, you control. You lock in that new setting. You create a new standard so it never drifts back.
So lean clears the obstacles, Six Sigma perfects the stride.
That's a great way to put it.
That brings us to the mechanism that actually allows for that level of control, the digital nervous system. The source material dives deep into IoT, the Internet of Things.
This is where the factory floor goes from just being mechanical to something almost biological.
I like that analogy, but here's my skepticism. Installing sensors on everything has to be expensive, right? A massive capital expenditure. Is it really just about knowing if a machine is on or off?
If that's all you're using it for, you are absolutely wasting your money. The strategic value is in the granularity. It's not just, is the machine running?
It's more than that.
It's what is the precise vibration frequency of the main spindle bearing.
So we're getting into predictive maintenance here.
Exactly. The source material highlights this as a major strategic shift. Traditional maintenance is preventative. You replace a part every 5,000 cycles, whether it needs it or not.
Which is really inefficient. You might be throwing away a perfectly good component.
Right. It's like replacing your car tires every 6 months, regardless of how much you actually drove.
Yeah.
But predictive maintenance uses that IoT data to find the unique fingerprint of an impending failure.
So the machine basically tells you, hey, I'm going to break in about 48 hours.
Precisely. The AI notices a tiny 0.5% shift in vibration or a 2-degree spike in operating temperature that it knows, from past data, correlates with a bearing failure.
But doesn't that create a data overload problem? I mean, if every machine is screaming about microvibrations, how do you filter the signal from the noise?
That is the challenge, absolutely. That's why the analyze part of that framework is so critical. You need algorithms that can filter out the normal operating noise and only flag the real anomalies.
But when it works...
When it works, the ROI is undeniable. You all but eliminate unplanned downtime. And in this industry, unplanned downtime is the ultimate sin.
It just kills the schedule. Okay, so we've got this digital brain monitoring the internal organs. But there was a segment in the source material that at first felt like a step backward to me.
Let me guess. The section on custom nameplates.
Yeah, it feels so analog. We're talking about stickers and little metal tags. But the more I read, I realized this isn't about decoration. This is about compliance and liability.
It is the product's passport. Think about it.
Yeah.
If you have this brilliant smart machine, but the label with the voltage rating, the safety warnings, the serial number, if that fades away because it was printed on cheap paper.
Then that machine is now a legal black hole.
Exactly.
You can't service it because you don't know the specs. You might fail safety inspections.
Precisely. The source details the materials necessary for this. Stainless steel, aluminum, polycarbonate. This is strategic enhancement because it ensures the product's identity survives whatever environment it lives in.
Nameplates for equipment need to withstand harsh conditions. That's the key phrase from the source.
It is.
If you're sending a pump to an oil rig, that little label is getting blasted with salt spray, chemicals, UV light.
And that's why they use processes like chemical etching or anodizing. You aren't just printing ink on the surface. You are physically altering the metal itself or trapping pigment inside an anodic layer.
So the data becomes part of the chassis?
Ideally, yes. That's the goal.
There was also a mention of pre-kitting labels. That sounded like a classic process efficiency play.
It is. Instead of a worker digging through a bin of 500 loose labels trying to find the right serial number, which is just a recipe for a mix-up, you kit the labels, the nameplate, the safety warning, and the branding logo for that specific unit all come in one packet.
Poka-yoke. Mistake proofing.
Exactly. You physically prevent the error of, say, putting a 110-volt label on a 220-volt unit.
Which would be a very bad, very explosive day for someone down the line.
A catastrophic day, yes.
So we've covered the process, the digital layer, and the identification. Now let's look at the actual substance of the product. The source material goes deep into material innovation.
This is where the physics of manufacturing gets really interesting. We're seeing a massive shift away from traditional heavy metals toward advanced polymers and composites.
The automotive example was striking cutting weight by 30 to 40% just by swapping metal for plastic. But I always wonder about the trade-off there. Are we just making things cheaper and, flimsier?
Not if you're doing it right. I mean, we're not talking about the plastic in a soda bottle. We're talking about high-performance engineering thermoplastics.
Yeah.
PEEK, Ultem, glass-reinforced nylons. These materials can handle heat and stress that would warp aluminum in some cases.
And carbon fiber. I feel like that's the go-to example for premium, but is it always the right strategic choice?
It really depends on the mission. Carbon fiber gives you that incredible strength-to-weight ratio. So for a drone or a high-end smartphone case where drop protection and weight are everything, it's unbeatable. But it's expensive, and it's harder to work with.
This is where it gets really sci-fi for me, though. The source mentioned smart materials, specifically self-healing polymers.
Yes, this stuff is fascinating.
It just sounds like magic. How does that actually work in a production context?
It's all chemistry. These polymers have reversible bonds in their molecular structure. So if the surface gets a minor scratch, the material can react, sometimes to a little heat, sometimes just to time, and the molecules literally rearrange themselves to close the gap.
So we aren't just extending the life of the product, we're fundamentally changing the maintenance model.
Completely. Imagine a car interior that heals its own scuffs from keys, or a phone screen that repairs minor scratches by itself. It maintains that premium feel of the brand for years longer than a traditional material could.
That's a huge brand enhancement.
Massive.
But having the best material in the world doesn't matter if you can't build it efficiently. This brings us to DFM design for manufacturing.
My favorite topic.
I know it is. But let's move past the basic definition. We know it means designing it so it can actually be built. The source gave a pretty dramatic example, reducing a product from 100 parts down to 50.
Think about the ripple effect of that. It's not just, oh, assembly is faster. You now have half the suppliers to manage, half the inventory to track, half the potential points of failure.
It simplifies the entire supply chain.
It does, but DFM gets even more granular. The source mentions using rounded corners instead of sharp angles. Now, to the average person, that looks like an aesthetic choice. Ooh, that looks sleek.
But on the factory floor, it's all about tool wear.
Exactly. If a CNC machine has to cut a sharp 90-degree internal corner, the tool has to stop, pivot, and dig in. It creates stress concentrations. It wears out the tool bit faster. A rounded corner allows the tool to just glide.
It cuts faster, the tool lasts longer.
And the part is actually stronger because you don't have that built-in stress riser.
So the designer in the studio thinks style, but the engineer sees cycle time reduction.
And the best products happen when those two people are in the same room talking to each other.
Okay, so we've designed it perfectly, we've chosen self-healing materials, the robots are watching the assembly, but how do we know it actually works? The final piece of this strategic stack is advanced tech and the safety net quality assurance.
The safety net is a great way to put it, but let's touch on the advanced tech first, specifically 3D printing.
Or additive manufacturing.
Right. And the source points out something really important here. We are not just printing prototypes anymore. We're printing final and use parts. The example they gave was patient-specific medical implants.
That's the ultimate customization.
You can't injection mold a knee replacement that fits only you without spending $50,000 on a unique mold. But you can 3D print it. That allows a level of product enhancement that was economically impossible just 10 years ago.
And on the machining side, holding tolerances within thousandths of an inch.
Which is standard for aerospace and medical, sure. But maintaining that tolerance across a 10,000 unit run, that's where the QA really comes in.
The source outlines 4 testing protocols: functional, durability, safety, and performance.
Right. Functional is binary. Does it turn on? Does it work? Durability is the torture test. Will it survive a drop? Safety is non-negotiable. Will it catch fire under load? And performance is about the promise. Does it actually do what the marketing team says it does?
And this all ties back to compliance, right? You mentioned ISO and ASTM standards.
These are the rules of the game. If you don't meet the ASTM standard for material strength or the ISO standard for quality management, you aren't a serious player. You're a liability waiting to happen.
The most interesting part of the QA section for me was this concept of the feedback loop. It's not just a gatekeeper at the end of the line saying pass or fail.
No, a gatekeeper is passive. Modern QA is active. If a part fails inspection, that data points immediately back to a specific step in the process. Part 504 failed because the wall thickness was too thin. That goes right back to the injection molder, who then adjusts the pressure.
So the failure of one single unit actually inoculates the rest of the batch against that same problem.
That is the goal. Continuous improvement. You use every failure to harden the process.
It seems like that's the through line for all of this. From lean to IoT to materials, it's all about tightening that loop.
It is. It's about visibility and control from start to finish.
So, to recap, we've stripped the waste. We've digitized the pulse of the factory. We've stamped the product's identity with chemical etching, and we've built the whole thing out of self-healing, space-age plastic.
A pretty good recipe for a solid product.
It is. But I want to leave you with a thought that kind of builds on that self-healing concept.
Go for it.
We have materials that can now repair themselves. We have machines that use AI to predict their own breakdowns and then schedule their own maintenance. We have automated feedback loops that correct defects without any human intervention.
I see where you're going with this.
Are we approaching a point where the product and the factory itself essentially takes care of itself? Where the human role becomes purely architectural?
The dark factory concept. Lights out manufacturing, fully autonomous.
Right. If the machine knows when it's sick and the material can heal its own wounds, are we moving toward a world where products are almost like biological entities that live and die on their own terms?
It's a distinct possibility. We might just be the designers who set the initial DNA,
Yeah.
and then we just step back and watch it all grow.
A fascinating and maybe a slightly terrifying thought to mull over.
Indeed.
That's it for this deep dive into strategic manufacturing. A big thanks to First Mold for the source material. We'll catch you on the next one.
Goodbye, everyone.